Hello guys, welcome back to our YouTube channel. For today, we will be solving the lab exercise 4 about switches and 7 segments display. For our first program, write a C++ program for the Arduino Uno as described below. Be sure to include an initial block of comments at the start of each program as well as comments throughout. Compile each program before lab and correct any errors that occur. The count should be initialized to 0 and shown on the 7-segment display and the computer screen. When the user presses the button, the count should advance and the new value should be displayed on the 7-segment display and the computer screen. The count should be mod to 10, 0 to 9 and repeat. Use the display digit function described presentation for this lab. Use the read button function provided in the presentation for this lab to allow for switch debounce. Now let's open Tinkercad to see the schematic diagram and demonstrate the circuit diagram for this challenge. As we can see, our segment A is connected to pin number 2. Our segment B is connected to pin number 3. Then our segment C is connected to pin number 4. Our segment D is connected to pin number 5. Our segment E is connected to pin number 6. Our segment F is connected to pin number 7. Our segment G is connected to pin number 8. We also use 220 ohms and 10,000 ohms resistors for this program. Our 7-segment display is also in common anode and connected to the 5 volts rail on the breadboard. While the pull-down resistor, which is 10k ohms, is connected between the button terminal that goes to pin 9 and the ground rail in the breadboard. Now let's see if it works. As we can see, it works. When we click the push button, the count advances to the next count. Now let me open the Arduino IDE to show you and explain the constructed code to be uploaded to the Arduino board for this challenge. The code begins by defining the pins for each segment of the 7-segment display and the pin for the button. The variables count, button state, and last button state are declared to keep track of the current digit, the current state of the button, and the last state of the button respectively. In the setup function, the button pin is set as an input, and the segment pins are set as outputs. Serial communication is initialized for debugging purposes. The initial digit is displayed on the 7-segment display and the initial count is printed to the serial monitor. In the loop function, the code checks if the button is pressed by calling the read button function. If the button is pressed, the count is incremented, wrap around to 0 after 9 using the modulo operation, and the new count is displayed on the 7-segment display. The updated count is also printed in the serial monitor. The read button function reads the current state of the button and checks if it has changed from the last recorded state. If the button state has changed and the button is in the high state, the function waits for 50 milliseconds to debounce the input and then returns true to indicate a button press. Otherwise, it returns false. And lastly, the display digit function sets the segment states based on the digit to display. Each case in the switch statement corresponds to a digit from 0 to 9. The segments are set to low or high to form the desired digit on the display. If an invalid digit is given, the count is reset to 0, and the display is updated accordingly. To see if it works, let's create the circuit diagram on the actual Arduino board while trying the codes we've created. Program 2, switch controlled up or down counter. Our first task is to connect a toggle switch and a 7-segment display on the Arduino Uno board. Next is to write a program to control an up or down counter using a toggle switch. That is, when switch is on, the counter counts upward 0 to 9, otherwise it should count downward 9 to 0. Next is to provide a 0.75 second delay for every count interval. And then, of course, run the program and verify that it works properly. So instead of a switch, we will be using a push button. Now let's open the Tinkercad to see the schematic diagram and demonstrate the circuit diagram for this challenge. As we can see, this is our segment A. Our segment A is connected to pin 13 of the Arduino board, while our segment B is connected to pin 12. Our segment C is connected to pin 11. Our segment D is connected to pin 9 here. And then our segment F is connected to pin 8. And last, our segment G is connected to pin 7. Our 7-segment display is also in common anode and connected to the 5 volts rail on the breadboard. This one. While the pull-down resistor, which is 220 ohms, is connected between the switch terminal that goes to pin 9 and the ground rail on the breadboard. Let's see if this works. As we can see, it works. When we hold the push button, the count goes downward, and when we release it, the count goes upward again. Now, let's open the Arduino IDE to show you and explain the constructed code to be uploaded to the Arduino board for this challenge. The code starts by defining the pins connected to each segment of the 7-segment display and the pin connected to the slide switch. The digits array contains the binary representations of the digits 0 through 9, where each bit corresponds to a segment on the display. In the setup function, the segment pins are set as outputs, and the slide switch pin is set as an input with an internal pull-up resistor, ensuring it defaults to a high state when not engaged. In the loop function, the code maintains a static variable count initialized to 9, representing the current digit to be displayed. Another static variable, last switch state, keeps track of the switch previous state to detect changes. The current state of the switch is read using digital read. The display is updated with the current count using the display digit function, which converts the digit to its corresponding segment pattern and sets the appropriate pins to high or low. A delay of 750 milliseconds is introduced to control the update rate. Depending on the switch state, the count is incremented or decremented. If the switch is high, the counter increases, wrapping around to 0 after 9. If the switch is low, the counter decreases, wrapping around to 9 after 0. This continuous loop ensures the display reflects the correct digit based on the switch's position. And for our last function, the display digit function, which converts the digit to its corresponding segment pattern and sets the appropriate pins to high or low, lighting up the correct segments on the display to show the current digit. Now, to see if it works, let's create the circuit diagram on the actual Arduino board while trying the codes we have created.
Let's now proceed to program 3, which is presettable up or down counter. Connect the toggle switch, 3 switches dip switch, and the 7-segment display on the Arduino Uno board. Write a program to ask the user to enter a predefined number to start the count from and the toggle switch input to determine whether to count up or down. The program can be switched from up or down interactively by switching the toggle switch. Provide a 0.75 second delay per count transition. Now, let's go to Tinkercad to see the circuit diagram and its schematic diagram. Here is the circuit diagram, and here is the schematic diagram. The difference on the requirement is that we don't have a toggle switch. Instead, we use two toggle buttons, which is for the up counter and for the down counter. Now that we have seen the circuit diagram and its schematic, now let's go to the code. So for that, we must declare the variables first. So first, we declared the dip 4, which is the 4 switches on the dip switch. And that pins or switch on the dip switch is connected to pin 2 to 5 of the Arduino Uno. Next is this output pins or for the 7-segment display, which is connected to pin 6 to 12 of the Arduino Uno. Next is the buttons, which are the replacement for the toggle switches, which are connected to the pin A1 and A2 of the Arduino Uno. The end current value is for when we want to add or minus the value, which is currently set as 0 because we don't have or we aren't currently adding or minusing 1 from the current value. And for the bool counting false, it is for checking if the counting is active. Next, we have the void setup. This code configures dip switch pins as inputs with pull-up resistors. This code configures output pins as outputs. This code configures button pins as inputs with pull-up resistors. And this initializes serial communication for debugging. Now let's go to the void loop. This code is for the dip switch states and decodes them as a binary number, or specifically a hexadecimal, because it reaches 0 to F. So yeah, it depends on the state if it is up or down. So next, this sets the current value to the start value from the dip switches. This determines output states based on current value. And this checks for button presses. And for the button presses, we have a 100 millisecond delay for the button debounce. Now let's go to the determine output function. This is for the 16 cases for the hexadecimal or binary, which is gonna be shown on the 7-segment display. So for case 0, it shows 1, and for case 15, it shows F. And the default is 0, 0. So for this set output pins, this is just for the, or first we declare the A to G, which is the segments on the 7-segment display, and where are they connected. So yeah. Next is for the check buttons. This checks if button A1 is pressed, and this is checked, and also for the A2. And if we press the button, it returns a value which is count up or count down, which is declared here. If we press the up button, it will go up, or the current value will go up by 1. And if we press the void countdown 2 button, it will go down by 1. Now that we are done showing and explaining the code, let's go try it first into Tinkercad and then show it on the Arduino Uno IDE itself later. So currently it shows F, which is 16, the current max value because the switches are down. So for the value of the switches, this one's value is 1, thus it minusing 1. This value is 2, thus it minusing 2. This one's value is 4, thus minusing 4 from the max value. And this one's value is 8, which is minusing 8 from the current value. So, for example, we want to go start at number 10. So, that is minus 6, or currently 5. 1 and 4, which is 10. So, if we want to count up, this is what the button you're gonna press is. Then, there. And go up again. It's gonna go C, D, E, and F. So this is also for the down. And let's go down it. Zero. There. So the only problem currently is that you cannot enter a number once you counted up or down. So we can just simply press restart and then enter a new value again. So let's start at 9. So We want to count up, it can count up. We want to count down, it can count down.
So now, let's proceed to demonstrate challenge number 3, problem 4. Traffic light circuit with 7-segment down counter. Connect 3 LEDs, green, yellow, and red, and 3 220 ohm resistors to the digital output pins of your choice. Write a program to simulate a traffic light where green LED is on for 9 seconds, yellow is on for 1 second, and red is on for 8 seconds. Provide synchronized timing to the down counter. The traffic light should operate forever. Run the program and verify that it works properly. Now, let's open the Tinkercad to see the schematic diagram and demonstrate the circuit diagram. This is the schematic diagram of the problem. And this is the circuit diagram of the problem. As you can see, the pins of the LEDs and the segments of the 7-segment display are connected to the respective pins in the Arduino board, together with 220 ohm resistor. The 7-segment display is a common anode. That's why the common segment is connected to the voltage source, which is 5 volts, to the Arduino Uno. Now, let me show you the codes we constructed for this program. We declared constant integer variable that were initialized with the pin numbers we use as output pins. Based on their names, the variable green LED has a value of 4, yellow LED has a value of 3, and red LED for 2. The constant integer A, or the segment A of the 7-segment display, is number 7, B for 8, C with a value of 9, D for 10, E for 11, F for 12, and G for pin 13. After that, we created array for the displaying of numbers in the 7-segment display. The nested arrays correspond to the value they will show to the display from 1 to 9. The first index is for segment A, and the last index is for segment G. Since the 7-segment display we use is common anode, 0 here is for turning on every segment, and 1 is for turning off every segment. Next, we created arrays for LED pins and segment pins so that our sketch will be shorter. Let's proceed to the setup function. Here, we use the for loop to configure the pins of the LED and segments. In the first for loop, we initialize I to 0. Then the loop will run as long as it is not greater than 2 or index 2. And I will be incremented by 1 after 1 cycle. We use the indexes of the LED pins array we initialized earlier to configure pins of the LED as output. In the second for loop, the configuration is just the same. The difference is that the loop will stop when I is greater than 6 or index 6. We use here the indexes of segment pins we initialized earlier to configure pins of 7-segment display as output. Now, let's proceed to loop function. At the first state of the loop function, we initialize green LED as high using digital write syntax. Then we use for loop with the initialization of I as 9. will stop until the value is not greater than 0 and will decrement by 1 for each execution. And this for loop is initialized like that so that during the execution of green light for 9 seconds, the 7-segment display will display countdown from 9 to 1. But it does not end here. You will need a nested for loop so that the program will be complete. The nested for loop contains variable j, wherein it is initialized as 0, will stop if j is not less than 7, and j will increase by 1 after each loop. Inside the nested for loop is a digital write syntax that configures the pins of the segment pins by calling their index one by one and configuring their state based on the nested arrays of the display numbers array. Then after the nested for loop is complete, there will be a delay of 1000 milliseconds or 1 second for the next instruction of the program. After the loop is done, there is another loop, for loop, that commands the display to stay turned off after the previous execution of this loop initializes I as 0. The loop will end if I reaches 7 and will iterate by 1 for each cycle. Inside it, there's a digital write syntax that configures every pins of the segment as high or turned off in common anodes. And after that, the green LED is set to low. The second and the third state of the loop function has the same pattern as the first state. The difference is that in the second state, for yellow LED, the value of I of the for loop is 1, and there's no calling of display number syntax since only 1 second display is needed. And in the third state, here, which is for the red LED, the value of I here is 8 for 8 seconds of running of LED and 7-segment display. Now, let's try to run the program and check if it works. So it works. The green LED is turning on for 9 seconds, synchronized with the 9-second down timer. Same with yellow LED that is on for 1 second, which also synchronizes to the down timer. And the red LED that is on for 8 seconds, that is also synchronizes to the down timer. So now, let's apply it to the actual Arduino board by imitating the circuit design and applying the code to the Arduino IDE. And it works. The circuit diagram and the set of codes we've created are correct.
Now let us head over to Challenge 4 Program 5. Design your own switch and 7-segment application. Construct the test circuit in your Arduino Uno board, run the program and verify that it works properly. To explain our own design of a 4-position dip switch and a 7-segment display application, let's take a look at the circuit in Tinkercad first. As you can see in the circuit view, the key components required by the challenge or program from the documentation are inserted here in the breadboard, which includes the 7-segment display, which is a common anode, and a 4-position dip switch. The yellow wires are connected to the segment pins of the 7-segment display towards the digital pins of the Arduino Uno, specifically from pin number 7 to pin number 13. The red wires are connected to the common anode pins of the 7-segment display, together with a 220 ohm resistor, towards the 5 volt or 5 voltage pin of the Arduino Uno. The upper part of the 4-position dip switch is connected to pins 3 to 6 in the Arduino Uno via the purple wires. Lastly, the lower part of the dip switch is connected to the ground of the breadboard and the Arduino Uno with the blue wires. To have a better understanding of our own design's functionality, let us start the simulation here in Tinkercad. Think of the dip switches as your inputs for a calculator which can only perform the basic operation of addition, with the 7-segment display showing the output of the calculation. Each of the switch here in the 4-position dip switch corresponds to its own number as input to the Arduino Uno. Their value will show up in the 7-segment display when they're turned on or up. If 2 or more switches are turned on, they are automatically added based on their values. For example, switching on number 1 and number 3 will display the value 4, which is the sum of 1 plus 3. Now let us check if each switch corresponds to their own values. For 1, there should only be the number 1 on the display. For number 2, for number 3, and lastly number 4. Now let us add up 3 numbers by turning on 3 switches. 2 plus 3 should display 5, and this current value added with 4 should be equal to 9. Okay, so it seems that our program is working. Achieving this functionality involves our own Arduino sketch. Let us view and explain our sketch on the Arduino IDE. For this portion of the sketch, let us talk about the segment pins. The integers A to G are assigned to specific digital pins on the Arduino. These pins control the segments of the 7-segment display. Dip switch pins, over here, S1 to S4 are assigned to digital pins that will read the state of the 4-position dip switch. In the state variables, S1 state to S4 state store the current state, high or low, of each switch. Now in this portion of the sketch, the pin modes. The pin mode function sets the segment pins as outputs and the switch pins as inputs with internal pull-up resistors. And for this portion of the sketch, is the display logic. This function takes a digit as input and turns on the appropriate segments by setting them low, assuming common anode configuration. The digital write statements are conditioned based on which segments should be lit for each digit. Next, this portion of the sketch, turn off segments. This function turns off all segments by setting them high. And this entire portion of the void loop first off, we have read switches. The state of each switch is read and stored in S1 state to S4 state. Conditional checks. Based on the state of the switches, a digit is displayed on the 7-segment display. Each combination of switch states corresponds to a different digit. The following conditional statements here, all the way down here. Delay and turn off. After displaying a digit for 1000 milliseconds or 1 second, the segments are turned off by calling turn off function. So that is all for the sketch. Now let us upload this compiled sketch to the Arduino Uno itself so we can see if the codes within this sketch or program does execute our own design or functionality as specified on the documentation for Challenge 4 Program 5. As you can see on this video demonstration using actual Arduino Uno and the key components mentioned, the 7-segment display views the outputs from 1 to 9 through the different combinations of the switches turned on and off. Therefore, the sketch we've used for designing our own switch and 7-segment application is correct. That's all for Challenge 4 Program 5.
So now, let's proceed to demonstrate challenge number 5, problem 6, 7-segment display marquee effect. Construct the test circuit on your Arduino Uno board which comprises of the following components: 2 pieces light-dependent resistor, 2 pieces of 7-segment display or dual display whichever is available. Create a program that will display a marquee effect of 2 messages. If LDR1 was enabled, it should display the message hello from left to right direction. Otherwise, display the message bye from right to left direction. Run the program and verify that it works properly. So now, let's open the Tinkercad to see the schematic diagram and demonstrate the circuit diagram. This is the schematic diagram for this problem. And this is the circuit diagram for this problem. As you can see, the circuit diagram is a little bit complicated. There are 2 7-segment display here, and they are different from each other. This at the right is common anode, while the left one is a common cathode display. Their common pins are connected to their respective pins, together with 220 ohm resistor. Each of the segment pins of a common anode 7-segment display is connected to pins 2 to 8 of the Arduino board, from segment A to G, and each of the segment pins of the common cathode 7-segment display is connected to pins 9 to 13 and pin A2 to A3 of the Arduino board, from segment A to G2. Now, let's proceed to the 2 photoresistor. One terminal of the photoresistor are connected to the 5V pins of the Arduino Uno. This and this. To the other terminal of the photoresistor, they are connected to 220 ohm resistor, and that is also connected to the ground and to the pin A0 and A1 as input pins. This and ito. Now, let's explain the constructed code for this program. First, we initialize constant integer arrays for the pins used for common anode display and common cathode display. The segment underscore display underscore 1 array, the one for common anode display, contains integer 2 to 8. And the segment underscore display underscore 2 array, the one for common cathode display, contains integer 9 to 13. and A2 and A3. Next, we initialize LDR underscore pin underscore 1 for A0 that is connected to the LDR1. And we initialize LDR underscore pin underscore 2 constant integer as A1 that is connected to light dependent resistor 2. Next is the constant integer LDR underscore threshold variable, wherein it holds the minimum threshold value for LDR activation. In this case, the threshold value should be 500 so that it will work in the actual Arduino. But in Tinkercad, we must use 1 as threshold value. Next, we created arrays hello and bye with nested arrays inside that are responsible for forming each letter for the words hello and bye that will be displayed to the 7-segment display. We also initialize idle array for the display of the 7 segments when both of the photoresistors are turned off. In the void setup function, we use for loop to configure the pins of the two 7-segment display with a variable of I that has an initial value of 0, must stop when it is not less than 7, and must increment by 1 per cycle. We also configure pins for light-dependent resistors as inputs. Now, let's go to the loop function. First, we initialize variables that will hold the received value from LDR1 and LDR2. We will get the values by using the analog read syntax. Now, let's go to the code where hello will show if LDR1 is turned on. Here, we created a conditional statement wherein if the value of LDR value 1 is greater than LDR underscore threshold, the program inside it will be executed. So first, let's assume the condition is true. We did here is that we first clear the displays using the digital write syntax. Remember that segment display 1 is for common anode and segment display 2 is for common cathode. Segment display 1 is configured to high since it is connected to common anode and we need it to be turned off, while segment display 2 is configured to low since it is connected to common cathode display. And the added delay here for 400 milliseconds. Next, this code will show the word hello by using for loops and digital write syntax. At first, the 7-segment display at the right side, which is the common cathode, will show the letter O first, then delay by 400 milliseconds. After that, the 7-segment display at the right side, which is the common anode display, will show now the letter O, and the letter L will show next at the left side, then delay by 400 milliseconds. Then next line, the letters LL will show with 400 milliseconds delay. Then EL will show at the next line with 400 milliseconds delay. Then HE with 400 milliseconds delay. And the screen at the left side will clear and H will be shown at the right side of the screen. This is inside the loop function, so it will continue forever unless the condition will be false. If the first statement is false, let's go to the second condition of the program inside the loop function. It says here that if LDR value 2 is greater than LDR threshold, it will perform the following codes inside it. First is, when LDR2 is on, the displays will be turned off first, just like what happened in LDR1. It has a delay of 400 milliseconds, and then, in this part, the letter B will show first at the right side of the screen, which remains left side clear, and it delays by 400 milliseconds. And then, the letter B will be shown now at the left, while letter Y is in the right side now, with a delay of 400 milliseconds, and letters YE will be shown after with 400 milliseconds delay. Lastly, letter E will be shown at the left side of the screen while the screen at the right side is clear now. And it will clear again, and it will repeat again and again. Since this is inside loop function, and will only be interrupted once the statement became false. If both of the statements above are false, it will only display line to the screens indicating that it is not in use. So with that, the word hello must be displayed to the screen from left to right if LDR1 that is connected to A0 is turned on, and the word bye must be displayed to the screen from right to left if LDR2 that is connected to A1 is turned on. So, let's try it in Tinkercad. At first, it is in idle mode so that the lines are the only ones showing on the screen. Now, let's try to turn on the LDR1. And it works. Now, let's try to turn on the LDR2. And it works too. So now, let's apply it to the actual Arduino board by imitating the circuit design and applying the code to the actual Arduino IDE to see if it really works in the actual one. And it works. The circuit diagram and the set of codes we've created are correct.